Very good morning to all of you. We're coming back to assessment of aortic valve. So, what are the modes and what are the views we have to see for the aortic valve examination? For the 2D examination, color Doppler and the aim mode, we have to see the mediasophageal aortic valve short axis view and mediasophageal aortic valve long axis view. And for the pulse wave and the continuous wave Doppler, for deep transgastric 5-chamber view and transgastric long axis view, because we can align with the flow. So the few points we have to remember that normal aortic valve area is 3 to 4 centimeter square, whereas the normal mitral valve area is 4 to 6 centimeter square. So it is measured by planimetry at the mediasophageal aortic valve short axis view at mid systole. So 3 cusp we can see that NCC, RCC and LCC, that's non-coronary cusp. This is the RCC, the right coronary cusp, it is left coronary cusp. It forms the Mercedes-Benz sign and the mediasophageal aortic valve long axis view. 2 cusp seen at the time, that's RCC is beside the RVOT and LCC and RCC which is variable. If we left rotate it, L for L, then we can see the LCC, and if we right rotate it, we can see the MCC. So this is all. This is the thing I was saying, that this is the mediasophageal aortic valve long axis view. So the RCC is behind the RVOT. This is constant, and this is the variable leaflet. This is the another loop showing the aortic valve short axis. This is the transgastric long axis. And this is the deep transgastric long axis, where we can these last 2 views we can align with the Doppler. So AR functional classification is a El-Khoury classification. There is actually 3 types of AR, just like Carpentier's MR classification. In type 1 there is normal cusp motion, and type 2 there is cusp prolapse, that is excessive motion, and type 3 is the cusp restriction. And if we go for 1A, 1B, 1C and 1D, so from above downward, from 1A the ascending aorta is involved, and 1B there is the sinotubular junction is involved, 1C is an annulus is involved, and also 1D is the leaflet itself, leaflet body is involved. So Doppler analysis, there is a few discrepancies we can see, that the Doppler analysis of AR jet, if anything like this is mentioned in the question, it's best done in the best option will be the deep transgastric or transgastric long axis, because Doppler analysis means we actually consider continuous wave and pulse wave Doppler. But if the question says that colored Doppler analysis is seen, the colored Doppler analysis of the AR is best done in the mediasophageal aortic valve long axis scene. And colored Doppler analysis of AR jet in presence of prosthetic mechanical mitral valve, it is based on in deep transgastric and transgastric long axis view. So Nyquist limit for any colored Doppler in a case of AR examination or any regurgitant examination should be 50 to 70 centimeter per second. Now jet height or LVOT height, by LVOT height, it actually underestimates the AR in case of eccentric AR, because we can see that this is an eccentric AR and this is the vena contracta, and this is the as the eccentric AR, this is only the jet height. So if we consider jet height and the LVOT height ratio, so we can see that this might be in the moderate range, but if you see the vena contracta, it will be in the severe range. So vena contracta is better than jet by LVOT height in case of the eccentric AR. Whereas in this image we can see this is a central jet, so we can see that this is a jet height area by LVOT area. So this is better for in case of the central jet. Now early diastolic flow reversal in descending thoracic aorta, it is a normal. So whenever we put a Doppler, in a pulse wave Doppler in a descending thoracic aorta, if it's a hollow diastolic flow reversal, that means in the entire diastolic period there is a flow towards your aortic valve, and your end diastolic velocity more than 20 centimeter per second, that is indicator of severe AR. Now more severe the AR, steeper is the AR curve and the lesser is the PHT. So in this image we can see this red line shows the LVOT velocity. So during diastole, normally there should not be any flow if there is no AR. But if there is AR, there is an increased flow in the LVOT. and the pressure gradient will get equalize later if there is mild regurgitation is there. If there is severe regurgitation, there is rapid deceleration of the pressure gradient, and it will, so the steep will be much more steeper in a case of severe aortic regurgitation. And also if we see the pressure curve in the LV, the pressure curve is also becomes equal to the aorta much faster in a case of severe AR. In this image also we can see the AR PST is the 314 millisecond. Now the problem of AR PST is there, that AR PST is influenced by LV compliance, SVR, the systemic vascular resistance, and any loading conditions, that is for example MR. So PST actually decreases with associated MR. So if we consider the gradation of the MR, so if the mild it is more than 500, moderate 200 to 500, and severe 200, less than 200. So in a case of if we example for this, if the compliance is concerned here, in a case of the if LV is low compliance, suppose the patient is having also diastolic dysfunction, so the pressure half time will be reduced to a lesser value, so the pressure will be equalized much faster, so PST will become less, though the AR is not that severe. Whereas if the patient is having high compliance of receiving chamber, if the suppose LV is already dilated, so that is why even if the AR is very high, if AR is very severe, the PST will be higher. So that is why PST is not considered as a routine echocardiography parameters for grading AR per se, because right now only these 3-5 parameters, echocardiographical parameters, are there for the grading AR, that is effective regurgitation orifice area, regurgitant volume, regurgitant fraction, vena contracta, and jet width by LVOT width. Now comes to aortic stenosis. This is a mid-esophageal short axis view we can see, and in this view we can do the planimetry of the aortic valve, and also the leaflet calcification and leaflet number we can see. Here you can see these aortic valve leaflets are grossly calcified, and the calcification is more in the RCC, and a trivial amount of calcification we can see in the NCC and the LCC. So this is a case of only pure AS. In a case of the bicuspid aortic valve, it is taken from our machine only. So this is a bicuspid aortic valve. This is short axis showing bicuspid aortic valve. Because bicuspid aortic valve, it is better to be commented during a mid systole, because the mid systole the opening becomes a fish mouth shaped. So that is why if the patient is having bicuspid aortic valve, it is better to delineate in the mid systole rather than in a diastole, where a RAFI can actually we misinterpret as it is a separate leaflet. So this is a unicuspid and a quadricuspid aortic valve example. This is a unicuspid valve. It is a quadricuspid aortic valve. So AS severity actually we see by maximum velocity and mean pressure gradient. Mark the word maximum and mean. So the PG mean is obtained by tracing VTI only. So if we trace the maximum velocity, it will actually by the Bernoulli's modified Bernoulli's equation, it will give you the actual value of maximum pressure gradient, not the mean pressure gradient. So 4 Vmax square is equal to maximum pressure gradient, which is not equal to pressure gradient mean. But even if we get a maximum pressure gradient, here is another modified formula, that is 2.4 into Vmax square. It will almost approximately give you the mean pressure gradient. So in this image we can see the Vmax is 4.1 meters per second, and max pressure gradient is 67. This 67 is being obtained by this 4 Vmax square, and this aortic valve VTI is another time is aortic valve VTI has been taken. So here you can see the mean pressure gradient, which is 39 millimeters of mercury. So anyone, suppose if the Vmax is more than 4 or the mean pressure gradient is more than 40, we can grade it as severe. So if the patient has, now another thing is to mention that we use the simplified Bernoulli's. There are three types of Bernoulli's. There is that is original Bernoulli's equation. Modified Bernoulli we consider 4V1 square, and the simplified Bernoulli we actually we ignore this V1. But if the patient has concomitant AR, this modified Bernoulli has to be taken, because here V1 is more than 1.5 meter per second, because the LVOT there is an increased amount of blood going through the LVOT during systole as well. So aortic valve area less than 1 centimeter square or 0.6 centimeter square per meter square indexed is, but it is not essential to grade severe AS. Rather, maximum velocity or mean pressure gradient is more important. So methods, we can see that these are, number one method is a planimetry. Number two method is the continuity equation, where with the cross sectional area of aortic valve into VTI of the aortic valve, we will give you the cross sectional area of LVOT into VTI of the LVOT. So by this equation I can deduce this. This is our query. So by this we can see the cross sectional area of aortic valve. But one thing to be mentioned, while using this continuity equation, this VTI of the aortic valve should be taken by continuous wave Doppler, and this VTI of the LVOT to be taken by pulse wave Doppler. And third method is the Doppler velocity index, where Doppler velocity index, there we can see, we can only grade that what the patient, if the patient has only severe AS or not. So here we can take two methods, that is simplified Doppler velocity index, that is LVOT Vmax and AV Vmax, or we can actually delineate the entire VTI. So LVOT VTI and aortic valve VTI. So both the method we can take. So by this method, if the value is less than 0.25, it is a severe AS. So most common cause AS overall, it is calcific, senile or degenerative, and if there is a younger age is mentioned in the question, then you can write the bicuspid aortic valve is the most common cause. And aortic valve area, another equation we follow, that aortic valve area Gauldin equation, this cardiac output divided by 44.3 into systolic ejection period into heart rate into root mean pressure gradient, that is used in cath lab. Now this mean pressure gradient is not echocardiographic pressure gradient. Now let us come to what is the fallacies of this pressure gradient measured in the cath lab. So Doppler derived gradients may be greater than catheter derived gradient. The cause is two. Number one is catheter derived peak to peak gradient is not the physiological phenomenon, because in a catheter derived, at first we measure this in the LV. We measure the maximum velocity, and we take out the catheter in the aorta, and we measure again the maximum velocity in the aorta. So but both the things are not occurring at the same time. So this is not a peak to peak gradient. This is actually peak to peak gradient, but actually the original gradient should be the gradient should be this. So but the catheter, the peak to peak pressure gradient, we actually what we measure is this. And second phenomenon that occurs is the pressure recovery, because the total energy is same, because the kinetic energy and the potential energy. So whenever the blood goes through that narrow orifice area, the kinetic energy increases, so potential energy decreases. So whenever the potential energy is what we measure actually. So because that is the pressure the blood exerts on the wall of the valve or on the aorta. When we take up the catheter outside, the some amount of kinetic energy is being reconverted toward the potential energy, but not all. So this amount of pressure recovery is not calculated. So this is the net pressure gradient which is being measured in the catheter based study, whereas this is the original gradient that is measured by echocardiographic. So echocardiographic gradient is better than catheter derived gradient. So this is a JASI 2020 this is a flow chart has been mentioned here. So it is better to mention for all of you that if you come across a aortic stenosis, if the mean pressure gradient is more than equal to 40 and aortic valve area is less than 1 centimeter square, it is termed as high gradient severe AS. There is no question in that. So if if there is a if you get aortic valve area less than 1 centimeter square and mean gradient less than 40, but that means these two are discordant. So aortic valve area gradient discordance occurs, then we will see that what is the stroke volume index. If the stroke volume index is more, that is more than 35, then it is a normal flow low gradient AS, or it is a low flow AS in case of the stroke volume index is less than 35 ml per meter square. Now if we get a low flow, then we will see the ejection fraction, it is less than 50%, then it is a classic low flow low gradient AS. And if it is a more than 50% of ejection fraction, it is a paradoxical low flow low gradient AS. And if it is a normal flow low gradient AS, then we will do a non-contrast MDCT AB calcium score. So right now we have not graded whether it's severe or not, mind that. So in a case of all these things, we will do a DAC and a non-contrast MDCT calcium score. Now after DAC, if the aortic valve area is more than equal to 1 centimeter square and mean pressure gradient is still less than 40, then it is a pseudo severe AS. Then if the DAC, after that the aortic valve area becomes less than 1 centimeter square, where after mean pressure gradient more than 40, then it is a severe AS. Then if the aortic valve area is less than 1 centimeter square and mean gradient is still less than 40, or stroke volume change in stroke volume less than 20%, it is indeterminate severity. So in these things we will do a aortic valve projection area. I am coming to later slide. And if it is less than 1 centimeter square, then it is a severe AS. If it is more than 1 centimeter square, it is a pseudo severe AS. And in this indeterminate severity, we will do a non-contrast MDCT AB calcium score. If it is less than 2000, less than 2000 and less than 1200 in case of male and female, it is non-severe AS. And it is more than equal to 2000 and more than equal to 1200 in case of male and female, it is severe AS. Now this is the aortic valve area projected. This is the formula. This is taken from the JASI to 2020. This is the aortic valve area. This is the D square into 0.785 plus this aortic valve area peak minus aortic valve area rest divided by flow peak flow minus peak.